Hello, my name is Kyu-Ho Lee. I am the founder and the CEO of Atomics AI. We use quantum mechanics and AI to predict protein ligand binding so that we can select better drug candidates and accelerate drug development with a higher success rate. To achieve reliable prediction, our AI learns from quantum mechanical simulations of molecules. Benchmark shows that the energy resolution of our approach is at least 4 times better than that of conventional approaches on the market, like docking or molecular mechanics using classical force field. Our AI predicts protein ligand binding 1,000 times faster than quantum mechanical simulation. We believe that our technology will reduce the false positive rates of virtual screening. Already there are more than 200 startups using AI in drug discovery. Among them, more than 100 companies are aiming to design and screen candidate molecules using all sorts of data from literatures and experiments. Several companies like Atomwise, Cyclica, Acelia, and Cloud Pharmaceuticals are using AI to predict protein ligand binding. However, prediction accuracy is still very sensitive to the target protein because experimental data are not abundant enough, not accurate enough yet. So there are unmet needs for reliable binding prediction. As is quoted here, one of the major limitations in drug design process is the inability of the existing docking programs to accurately estimate binding affinities. And improving the predictive accuracy of scoring functions in various docking programs is a major challenge to computational chemists, and it would help this method to enable a greater impact in lead identification and optimization stage of drugs discovery. QM can provide accurate prediction. However, quantum mechanical simulation has its own limitation on its size. Quantum mechanical simulation cannot simulate proteins because the cost increases rapidly as the number of atoms increases. We solve this problem by using linear scaling AI. So how bad are conventional approaches, and how good is our approach? To assess the interaction between molecules, we compare the binding energies of these molecular pairs in S22 dataset. For unbiased assessment, the S22 set includes hydrogen-bonded types, van der Waals types, and mixed-type molecular bindings. The predicted energies are visualized in these plots. For each molecular pair, the accurate binding energy is given as X value and calculated energy as Y value, and represented as a dot. Accurate prediction sits on the diagonal line. Let's look at the conventional method first. As you can see here, most of the dots are way off from the diagonal line. For example, the dot farthest to the right is for uracil dimer, and predicted binding energy is a half of correct value and 10 kcal per mole off. Root mean squared error of all 22 pairs is 3.29 kcal per mole. In contrast, our QM quantum mechanical simulations RMSE is only 0.78 kcal per mole. So the energy resolution of our approach is about 4 times better than that of conventional approaches on the market. And our trained AI runs 1,000 times faster than quantum mechanical simulations and predicts the energy accurately. As you can see here, 10 hours of recalculation can be done in 36 seconds. That is about half a second per molecule. And the mean absolute error of all 66 energies is less than 0.07 kcal per mole. So far, we have shown the accuracy and efficiency of our QM plus AI approach for small organic molecular pairs. And now we are generating dataset for amino acids to predict protein peptide binding. Finally, here is our 4-year roadmap. We plan to finish amino acid AI by the end of this year and enter the peptide drug market next year. Then we will expand to neoantigen and small molecule market by 2023. Thank you. I appreciate your time, and if you have any questions, feel free to contact me. Thank you. Bye.